Right now, at this very moment, as you watch these light rays striking the magnified eye, similar tiny beams of light are entering your own eyes. And it's by our eyes that we are able to gain a great part of our knowledge. Nature has located the eye close to the brain so that its messages may arrive there quickly. Nature has also provided ample protection for this very delicate organ. Here, with the outer coverings removed, we see the eyeball completely surrounded by a layer of soft, fatty tissue and placed within the bony orbit, where it lies protected against sudden jolts. Seen from the side, the protected position of the eyeball within its funnel-shaped eye socket is shown still more clearly. Once again, we see the fatty cushion which protects it on all sides. Note this white stalk, which is the optic nerve, and also these muscles, which move the eyeball. This is the empty eye socket within the skull, with its bony walls inside and the rim of the bony orbit in front. By gradually restoring the outer portions of the skull and also the covering tissues, we can now realize the location of the entire eye in relation to the outline of the face. Another important safeguard to the eye is the tear gland, which secretes the tear fluid. This is an effective germicide which drains through the tear ducts into the nose after flushing and cleaning the entire eye surface. The eyeball itself has a white, glistening surface. Its front part bulges and forms a highly transparent window. In this sectional view, the capsule of the eyeball is seen to have 3 layers. This thick, tough outer layer is called the sclera and serves to protect the delicate structures within. This transparent bulging portion is called the cornea. Notice also the crystalline lens, which is one of the main features of the eye mechanism. The second layer is called the choroid. It consists of 3 different belts or zones. The first zone is called the choroid proper and is the part that carries nourishment to the tissues of the eye. The next zone is called the ciliary body. This is a broad ring-shaped band of thin muscle fibers which play a very active and vital part in the visual adjustment of the eye. The third zone is the well-known iris, which expands and contracts the pupil much like the diaphragm of a camera. The iris will soon be described in greater detail. Here is an outside view of the entire choroid, which shows the dense network of arteries and veins carrying nourishment to the eyeball. You can also see the shape of the ciliary body and the iris. The innermost layer of the eyeball is the retina, a very delicate membrane. The retina is actually a part of the optic nerve which transmits the light impulses to our brain. The retina is the most important and complex structure in the eyeball. Magnified many hundred times, the retina is seen to consist of this complicated arrangement of rods and cones, which convert light waves into nerve impulses in some manner which even science of today cannot fully explain. Between the lens and the cornea is the aqueous humor, consisting mostly of water and a little salt. This larger space within the eye is filled with the vitreous humor or body, consisting chiefly of water with some salt and albumin. The vitreous humor is really a highly transparent jelly and plays a very important part in the act of visual adjustment. Thus, light rays entering the eye must pass in succession through first the cornea, second the aqueous humor, third the pupil, fourth the crystalline lens, and fifth the vitreous humor in order to reach their destination, the retina. Now, just how do light rays act to form a clear picture within the eye? First, let us realize that light rays reflected from any object radiate in all directions, and that as an object moves farther away from us, the angle between the rays that enter our eyes grows smaller and smaller. And finally, when the object has reached a distance of 15 feet or more, the rays entering our eyes are practically parallel. Now, nature has provided that parallel rays shall produce a sharp image upon the retina without any effort, and, as one may say, with the eye in a state of complete relaxation. But if a distant object approaches the eye, the angle between entering rays again grows larger. This increasing angle changes the direction of the light rays as they pass through the lens, so that the sharp image falls behind the retina. As a result, the image upon the retina tends to become blurred. This blurring causes a response or reflex within our brain, which brings about harmonious internal adjustments of all parts of the eye. This adjustment is called accommodation. Accommodation restores the sharply focused image with marvelous speed and accuracy. This is all the more remarkable because the distance between lens and retina is fixed, and the lens itself must change its shape. Now compare this with the focal adjustment of a camera. Here the lens remains unchanged, but the film itself is moved until it reaches a sharp focal image. It is also necessary that both our eyes be fixed upon the same point in order that we may see an object clearly. Thus, as an object approaches us from a distance, our eyeballs turn accordingly. This movement is called the convergence of visual axes. This action is shown here as the object approaches and recedes. Here, in addition, we see the lenses accommodating their optical shape under the combined influence of blurred image and eyeball movement. And now let us look at this highly enlarged view of the lens itself. It has a soft, yielding body and is as transparent as glass. But it also has a firm, ball-shaped central core or nucleus. It is contained within a thin, elastic membrane and is suspended all around by a spoke-like arrangement of delicate threads or ligaments. The lens itself lies between two liquids. These liquids can exert pressure. All liquids cannot be compressed. You may ask then, how is this soft, pliable body of the lens made to take on the different degrees of convexity necessary for accommodation? In order to explain this, let us again call attention to the important ciliary muscle, which we see here in the diagram. This muscle is shaped like a broad ring which can expand and contract. Whenever it does contract, it must press upon the non-elastic vitreous humor. This liquid is confined within the rigid capsule of the eyeball and must, therefore, exert pressure upon the lens. Now, the lens as a whole cannot give way against the equally non-elastic aqueous humor and its confining cornea. So the only part which can possibly yield to the pressure of the vitreous humor or body is the soft substance of the lens. This lens substance is thus molded into an even curve against the rigid ball-shaped core, thus forming this highly convex bulge which science has called lenticonus. So whenever the image upon the retina becomes blurred, the brain automatically causes the ciliary muscle to contract or to relax until the lens has attained just the right shape to restore a sharply defined image upon the retina. This is the remaining portion of the choroid, called the iris, with its central opening, the pupil. Like the diaphragm of a camera, the iris regulates the amount of light and sharpens the image upon the retina. The iris acts automatically, and so is an important link in the process of accommodation. Its action is caused by two sets of delicate muscle fibers within the iris itself. These muscles are shown here in simplified diagram. These spoke-like radial fibers pull the pupil open. This ring-shaped muscle around the pupil closes it. In this side view, we see the opening and closing of the pupil, so that we may more clearly understand another important part played by the iris. Whenever demanded by conditions, the lens acquires this peculiar bulge called lenticonus. This cone-shaped curve at first causes light rays to become distorted into aberrations upon the retina. As a result of these distortions, the pupil now contracts until the diffused rays have been shut away and only a clear image remains upon the retina. These interesting mechanics of the lens are not generally known, and the facts presented here have only recently been accepted by science. It is well for us to know that our eyes are one of our greatest gifts of nature and are indeed worthy of our constant care and protection.